in a controlled environment, while an electric engine relies on electrical energy to produce motion. Now, the energy generated needs to be transferred to the wheels, task executed by the transmission system. The transmission acts as a mediator, modulating the engine's power to ensure the wheels operate at an optimal speed. It's akin to a maestro conducting an orchestra, ensuring each component operates in sync to produce a melodious performance, or in this case, a smooth drive. Shift our gaze to the chassis, the skeletal framework that not only supports the vehicle, but also hosts vital systems like the suspension and steering systems. The suspension system is like the legs of the vehicle, absorbing shocks and maintaining contact with the road, while the steering system is the navigator, directing the vehicle as per the driver's input. Next in line is the braking system, the guardian angel that ensures safety by decelerating the vehicle when needed. A precise and responsive brake system is paramount to avoid calamities and ensure a safe journey. As we traverse further, we encounter the electrical system, a network of circuits and devices that cater to various functions like lighting, ignition, entertainment, and much more. In modern vehicles, the electrical system is also intertwined with the vehicle's computer systems, orchestrating advanced functions and features that enhance safety, efficiency, and the overall driving experience. Venturing into the realm of control systems, we find an array of sensors, actuators, and control units that constantly monitor and adjust the vehicle's performance to ensure optimal operation. These control systems are the brain behind the intelligent features we find in modern vehicles, ranging from adaptive cruise control to autonomous driving capabilities. The fuel system, another crucial component, is responsible for storing and supplying fuel to the engine. It is like the digestive system of the vehicle, providing the necessary fuel for the engine to operate efficiently. Now, as we delve deeper into the automotive anatomy, we'll stumble upon numerous other systems and components, each with a unique function, yet all intertwined in a complex dance that drives the modern automobile. The automotive landscape is also heavily influenced by external factors like governmental regulations, environmental concerns, and the incessant quest for innovation. These factors play a pivotal role in shaping the design, operation, and evolution of automotive systems. Furthermore, the automotive sector doesn't operate in isolation. It's intertwined with various other sectors like the energy sector, the tech sector, and the infrastructure sector. The evolution of automotive systems is also synonymous with the evolution of associated industries, a symbiotic relationship that propels the wheel of innovation further. As we progress through this seminar, we will dissect each of these systems in meticulous detail, exploring their design, operation, innovations, and their impact on the overall automotive landscape. This exploration will not only enrich our understanding, but also foster a holistic perspective that transcends the technical realm, delving into the societal, economic, and environmental impacts of automotive systems. Each lecture henceforth will be a deep dive into a specific system or component, unraveling the complex engineering while also exploring the challenges, innovations, and the future trajectory of automotive systems. So, as we steered into the heart of automotive engineering, I encourage you to foster a curious mind, engage in discussions, and explore beyond the confines of the classroom to truly grasp the essence and the broader impact of automotive systems. So gear up as we embark on this intellectual expedition, unraveling the automotive enigma, one component at a time. Today marks our initial foray into the realm of internal combustion engines, ICs, a pivotal cornerstone in the automotive domain. The internal combustion engine is a marvel of engineering that converts fuel into mechanical energy, propelling automobiles across distances, and has been the primary power source for vehicles for over a century. We commence our exploration with a glimpse into the basic principles underpinning the operation of ICEs. At its core, an internal combustion engine operates on the premise of converting chemical energy housed within fuel into mechanical energy through a series of controlled combustion. This process unfolds within the engine cylinders when fuel mingling with air is ignited by a spark plug, culminating in a combustion that generates a high pressure gas, which in turn propels the pistons. These reciprocating pistons are connected to a crankshaft, and as they move, they rotate the crankshaft, producing the mechanical energy that drives the wheels of the vehicle. Now let's touch upon the different types of internal combustion engines. Primarily, we have the petrol, gasoline engines and diesel engines. The fundamental difference between these two lies in the method of igniting the fuel-air mixture. In gasoline engine, a spark plug provides the spark needed for combustion, while in diesel engines, the compression of the air in the cylinder raises the temperature to a point where the fuel auto ignites. Further categorization of ICEs can be done based on the number of strokes or cycles the piston completes during the operation. The most common are the 4-stroke and 2-stroke engines. The 4-stroke engine encompasses intake stroke, compression stroke, combustion or power stroke, and exhaust stroke. Each stroke serves a unique purpose, and together they contribute to the complete cycle operation. On the other hand, the 2-stroke engine accomplishes the same cycle in just 2 strokes, making it more compact but less efficient and more polluting compared to its 4-stroke counterpart. The arrangement of cylinders within the ICE also delineates different engine configurations. The inline, V-type, and flat or boxer engines depict varying arrangements of cylinders, each with its unique set of advantages and trade-offs concerning compactness, balance, and the ease of manufacturing. As we delve into the nuances of internal combustion engines, it's evident that this conventional power source encapsulates a blend of intricate engineering, thermodynamics, and material science. The design and operation of ICEs have evolved over time, endeavoring to enhance efficiency, reduce emissions, and comply with the ever-stringent environmental regulations. These endeavors have led to the development of technologies like fuel injection systems, turbocharging, variable valve timing, and exhaust gas recirculation, among others, all aimed at optimizing the performance and reducing the environmental footprint of ICEs. As we proceed in our subsequent session, we will dive deeper into the operational intricacies, component analysis, and the technological advancements that have marked the journey of internal combustion engine. Moreover, we'll explore the transition towards more environmentally benign power sources like electric and hybrid engines, and how this transition is shaping the future of automotive engineering. As we continue our exploration into the world of internal combustion engines IS, today we venture deeper to understand the core components and the performance metric that define its powerhouses. We begin with the heart of the engine, the cylinders. Each cylinder is a chamber where the combustion process unfolds. The fuel-air mixture is ignited, creating high-pressure gas that moves the piston housed within. The number I cylinders in the engine, often referred to as inline 4, V6, V8, and so on, significantly influences the power and smoothness of an engine. More cylinders generally mean more power and a smoother operation. Now, onto the pistons. Pistons are disc-shaped components that move up and down within the cylinders, converting the energy from the combustion into mechanical motion. The movement of pistons is harmoniously synchronized with the opening and closing of engine valves, ensuring the timely ink of the fuel-air mixture and the expulsion of exhaust gases. Now, onto the pistons. Pistons are disc-shaped components that move up and down within the cylinders, converting the energy from the combustion into mechanical motion. The movement of pistons is harmoniously synchronized with the opening and closing of engine valves, ensuring the timely intake of the fuel-air mixture and the expulsion of exhaust gases. The crankshaft is another pivotal component. It's connected to the pistons via connecting rods, and as the pistons move, they rotate the crankshaft, converting the reciprocating motion of the piston into rotational motion that ultimately drives the wheel. Let's now touch upon the valve train, which encompasses valve, camshaft, and timing belt or chain. The valves control the flow of the fuel-air mixture into the cylinders and the expulsion of exhaust gases out of the cylinders. The camshaft, operated by the timing belt or chain, controls the opening and closing of valve, ensuring they operate in perfect sync with the piston's movement. Now, onto the performance metrics. The efficiency of an internal combustion engine is often guided by its brake horsepower gap, which is the engine's output before losses like friction are accounted for. Torque, on the other hand, is the rotational force produced by the engine, a crucial factor for acceleration and towing capacity. Fuel efficiency, measured in miles per gallon m/l per 100 kilometers, indicates how effectively the engine converts fuel into distance traveled. Additionally, emissions are a critical metric, especially in the contemporary narrative of environmental sustainability. Engines are scrutinized for their emissions of pollutants like carbon monoxide, hydrocarbons, and nitrogen oxides, driving the evolution of emission control technologies and alternative fuel options. The understanding of these components and metrics is paramount as they provide a lens to evaluate, compare, and innovate in the realm of internal combustion engines. They are the lexicon that engineers, designers, and policymakers employ to discuss, evaluate, and advance the automotive engineering domain. As we transition in our subsequent lectures towards modern advancements in alternative powertrains, a solid grasp of the traditional internal combustion engine's workings provides a robust foundation. It equips us with the knowledge to appreciate the strides made in automotive engineering and the challenges and opportunities that lie ahead as we steer towards a more sustainable and efficient automotive future. So, as we rev up our intellectual engines, the journey we are on will unveil not just the mechanics, but the impact and the broader narrative intertwined with automotive engineering. Stay tuned, stay engaged as the road ahead is filled with intriguing discussions, eye-opening discoveries, and a plethora of knowledge waiting to be unraveled. Today, we embark on a new chapter of our automotive journey as we delve into the world of electric and hybrid vehicles. This exploration begins at a crucial juncture where the traditional norms of automotive engineering intersect with the imperative of environmental sustainability. Electric vehicle, or EVs as they are commonly known, represent a significant leap towards reducing the automotive sector's carbon footprint. Unlike their internal combustion engine counterparts, EVs are propelled by electric motors powered by electricity stored in batteries. This shift from fossil fuels to electricity has far-reaching implications, not just for vehicle design and performance, but also for the broader energy landscape. The heart of an electric vehicle is this battery. The battery stores the electric energy that powers the electric motor. The capacity of the battery, often measured in kilowatt hours, significantly impacts the vehicle's range or the distance it can travel on a single charge. The electric motor, on the other hand, converts electrical energy into mechanical energy, driving the wheels and propelling the vehicle forward. Now let's touch upon the advantages of electric vehicles. First and foremost is the reduction in emissions. Electric vehicles produce no tailpipe emissions, which is a significant advantage in the quest to combat air pollution and climate change. Moreover, electric vehicles are known for their quiet operation and smooth acceleration, enhancing the driving experience. Furthermore, electric vehicles often boast lower operating costs. They require less maintenance as they have fewer moving parts compared to traditional ICE vehicles, and the cost of electricity can be lower than that of gasoline or diesel, especially when home charging is utilized with solar power systems. However, electric vehicles also face challenges. The initial cost of EVs can be higher due to the cost of the batteries. The charging infrastructure is still in development phase in many regions, and the charging time is longer compared to the time it takes to refuel an ICE vehicle. Moreover, the range anxiety or the fear of running out of charge before reaching the charging station is a real concern for many potential EV buyers. Despite these challenges, the trajectory of electric vehicles is promising. Advancements in battery technology are continually extending the range of EVs, reducing charging times, and lowering costs. Moreover, the growing awareness of environmental issues and the incentivization of EV purchases through governmental policy are driving a significant shift towards electric mobility. As we move further into the electrification of the automotive sector, the landscape of vehicle design, energy, infrastructure, and automotive manufacturing is evolving. Today's discussion lays the groundwork for a deeper understanding of the technologies, challenges, and opportunities associated with electric vehicles, setting the stage for our next lecture, where we will delve into the hybrid vehicle technology, a bridge between the traditional ICE vehicles and the EVs. As we traverse further into the realm of electric mobility, today's discourse will pivot towards hybrid vehicles, a significant waypoint or automotive expedition. Hybrid vehicles, as the name implies, are a blend of traditional internal combustion engine, electric vehicle technology, and electric vehicle technology. They harness the strengths of both worlds to offer a more fuel efficient and environmentally friendly alternative to solely gasoline or diesel powered vehicles. The linchpin of hybrid technology is its ability to recuperate and store energy which would otherwise be lost in traditional vehicles. For instance, during braking, a process known as regenerative braking converts some of the kinetic energy lost into electrical energy, which is then stored in the battery for later use. This mechanism significantly enhances fuel efficiency and is a hallmark of hybrid technology. Let's delve into the different types of hybrid vehicles. Primarily, we have the series hybrid, parallel hybrid, and plug-in hybrid. In the series hybrid, the gasoline engine generates electricity for the electric motor, charges the battery, but it doesn't directly drive the wheels. In parallel hybrid, both the gasoline engine and the electric motor can drive the wheels, often working together to optimize efficiency. The plug-in hybrid, on the other hand, has a larger battery that can be charged from an external source, providing a longer electric-only range compared to other hybrids. Now let's touch upon the pivotal component of hybrid vehicles. The electric motor in a hybrid vehicle serves dual purposes. It drives the wheels either alone or alongside the gasoline engine and acts as a generator to recover energy during regenerative braking. The battery stores this recuperated energy and the energy generated by the gasoline engine, providing a reservoir of electric power to be used when needed. The control system in a hybrid vehicle orchestrates the operation of the gasoline engine and the electric motor to ensure optimal efficiency and performance. Transitioning our focus to the broader impacts, hybrid vehicles serve as a conduit to alleviate some of the challenges associated with full electric vehicles, such as range anxiety and charging infrastructure. They provide a more accessible pathway for many individuals to adopt greener automotive solutions while concurrently offering the familiar characteristics of traditional ICE vehicles. Moreover, hybrid vehicles play a pivotal role in the ongoing narrative of reducing vehicular emissions and fuel consumption. They offer a pragmatic step towards a more sustainable automotive landscape, aiding in the mitigation of greenhouse gas emissions and the reduction of the automotive sector's carbon footprint. The advent of hybrid technology also signifies a broader trend within the automotive industry towards embracing innovative solutions to address the challenges of modern mobility. As we delve deeper into this realm in the subsequent lectures, we'll unravel more nuanced technologies and the evolving dynamics of automotive engineering. So, as we continue to navigate through the multifaceted domain of electric and hybrid vehicles, let's endeavor to grasp the underlying technologies, appreciate the evolutionary strides, and envisage the promising horizon of automotive innovation that beckons. Today, we delve into the intricacies of transmission systems, a pivotal cog in the automotive machinery that plays a crucial role in managing the power generated by the engine and ensuring it's effectively utilized to drive the vehicle. The transmission system acts as a bridge between the engine and the wheels, modulating the engine's power to ensure the wheels operate at an optimal speed. It's a marvel of mechanical engineering that has evolved over the decades to meet the escalating demands for efficiency, performance, and ease of operation. Let's commence with the fundamental understanding. The primary function of a transmission system is to provide a means to vary the torque and speed between the engine and the wheels. When a vehicle accelerates, the transmission system ensures that the engine operates within optimal range of speed and torque, ensuring the vehicle moves smoothly and efficiently. Now, on to the different types of transmission systems. The most common types are manual transmission, automatic transmission, and continuously variable transmission. Manual transmissions are the oldest type, requiring the driver to manually select the gears and operate a clutch to engage and disengage gears. It provides a direct connection between the engine and the wheels, allowing the driver to control the power transfer. Automatic transmissions, on the other hand, take over the task of gears shifting from the driver, ensuring the vehicle operates at an optimal gear ratio without any input from the driver. They provide ease of operation, making driving less demanding, especially in traffic conditions. The continuously variable transmission column is a modern innovation that eliminates the traditional gears altogether. Instead, it continuously varies the transmission ratio, effectively providing an infinite number of gear ratios to ensure optimal engine performance under different driving conditions. Each type of transmission has a set of advantages and drawbacks concerning efficiency, performance, and ease of operation. The choice between them often hinges on the specific needs and preferences of the driver, as well as the design and intended use of the vehicle. Transmission systems are not just about gears and clutches. They encompass a plethora of components like hydraulic systems, electronic controls, and sensors that work in harmony to ensure the seamless transfer of power from the engine to the wheels. As we delve deeper into the mechanics and electronics of modern transmission systems in the subsequent lectures, we'll explore the technological advancements that have significantly enhanced their efficiency and performance. We'll also touch upon the emerging trends like the integration of electric motors and hybrid transmission systems, which are blurring the lines between traditional and modern transmission technology. So gear up as we shift into the detailed exploration of transmission systems, unraveling the complexities and appreciating the engineering prowess that underpins this essential aspect of automotive technology. As we continue our exploration into the realm of transmission systems, today's discourse will delve deeper into the components and performance metrics that characterize these indispensable systems. Let's initiate our discourse with the key components. Gears. At the heart of the transmission system are the gears. They come in pairs and are designed to transmit rotational motion from one shaft to another, varying the speed and torque in the process. The arrangement and size of these gears dictate the number of speeds the transmission can provide. Clutch and manual transmissions. The clutch is the component that engages and disengages the engine from the transmission to enable gear changing. It's the mediator that ensures a smooth transition between gears. Torque converter. In automatic transmissions, the torque converter takes the place of the clutch, providing a variable amount of torque based on the speed of the vehicle. Planetary gear sets. In automatic transmissions, these complex gear sets allow for multiple gear ratios to be achieved, enabling the vehicle to accelerate and decelerate smoothly. Hydraulic system. This system operates the clutches and bands needed to control the planetary gear sets, making automatic shifting possible. Electronic control units, modern transmissions, are often managed by an ECU that monitors various parameters to determine the most efficient gear for the current driving conditions. Now transitioning to performance metrics, the efficiency of a transmission system is paramount. An efficient transmission transfers the maximum amount of energy from the engine to the wheels, ensuring optimal performance. The gear ratio, which is the ratio of the input gear speed to the output gear speed, is a critical metric that impacts the vehicle's acceleration and top speed. Moreover, the shift quality, which refers to the smoothness and quickness of gear changes, significantly affects the driving experience. Modern automatic and CV transmissions often excel in providing smooth, seamless shifts, enhancing the driving comfort. Furthermore, the durability and maintenance requirements are critical consideration. A well-designed and well-maintained transmission can significantly extend the lifespan and overall reliability of a vehicle. Lastly, the advent of electronic and hydraulic systems has led to the development of more sophisticated and efficient transmission systems. The integration of electronic controls has enabled features like adaptive shifting, where the transmission adapts to the driver's behavior and the driving conditions to provide optimal performance. The evolution of transmission systems mirrors the broader narrative of automotive engineering, striving for enhanced efficiency, performance, and user-friendliness while concurrently embracing modern technological advancements to meet the escalating demands of contemporary mobility. As we venture forth in our automotive saga, the complexities and the ingenuity encapsulated in transmission systems serve as a testament to the remarkable engineering prowess that propels the automotive domain forward. So, as we shift gears into the forthcoming topics, let's carry forth the knowledge garnered and the curiosity kindled into unraveling further marvels of automotive engineering. as we steer our academic voyage towards another cornerstone of automotive engineering. Today we'll delve into the domain of suspension systems. The suspension system is akin to the legs and feet of a vehicle, providing the necessary support and absorption of road irregularities, ensuring a smooth and controlled ride. At its essence, the suspension system has three primary objectives: to support the vehicle's weight, to absorb shocks and bumps from the road, and to allow the driver to maintain control of the vehicle. It's a blend of mechanical and hydraulic components working in harmony to achieve these objectives. Let's begin by understanding the core components of a suspension system. Springs are the fundamental components that bear the weight of the vehicle. They absorb and dissipate energy from road bumps, providing the initial layer of ride comfort. Shock absorbers, also known as dampers. Shock absorbers control the movement of the springs, damping the oscillations induced during the travel over rough terrain. Struts. A strut combines the function of a shock absorber and a spring in a single unit, providing both damping and structural support. Anti-roll bars. These components connect the left and right sides of the suspension, helping to maintain stability and reduce body roll during cornering. Control arms and linkages. These mechanical linkages connect the suspension to the chassis, allowing for relative motion while maintaining correct alignment of the wheels. Now, onto the different types of suspension systems. Primarily, we have independent suspension. In this setup, each wheel can move independently of the others, providing better ride comfort and handling. Dependent suspension. Here, the movement of one wheel is related to the movement of the other, often used in the rear of trucks and large vehicles due to its simplicity and ability to carry heavy loads. Semi-independent suspension. This is a middle ground where the wheels are interdependent but not entirely so, allowing for a compromise between handling and ride comfort. Each type has a set of advantages and is suited for different types of vehicles and driving conditions. The design and operation of suspension systems are a testament to the complex interplay of mechanical engineering, materials science, and physics. It's an area ripe for innovation with modern advancements like adaptive and active suspension systems, which adjust in real time to change in road conditions and driving dynamics, significantly enhancing the vehicle's performance and comfort. As we bounce into the intricacies of these systems in our ensuing discussions, we'll unearth the engineering marvels that ensure our journeys on the road are smooth, controlled, and safe. Today's discourse lays the foundation for a deeper understanding of how suspension systems contribute to the holistic performance and safety of a vehicle. So, as we roll into this new terrain of automotive knowledge, let's brace ourselves for an enlightening journey through the dynamics of suspension systems. As we continue to traverse the terrain of suspension systems, today's discourse will delve deeper into modern advancements, performance metrics, and the broader implications of suspension design on vehicle safety and comfort. Let's initiate our discussion with modern advancements in suspension technology. Adaptive suspension systems. These systems automatically adjust the suspension setting based on the driving conditions. They utilize sensors and electronic control to optimize the ride comfort and handling dynamically. Active suspension systems. A step further, active suspension systems can independently adjust the suspension at each wheel, providing a superior level of control and comfort. They can even anticipate road conditions using cameras and other sensors, adjusting the suspension in advance to mitigate the impact of road irregularities. Magnetic ride control. This cutting-edge technology uses magnetohelical dampers, whose damping rates can be adjusted by varying the magnetic field within the damper. This allows for real-time adjustments to the suspension settings, providing an optimal balance between ride comfort and handling. Air suspension. Utilizing air springs instead of conventional coil springs, air suspension systems provide a plush ride and the ability to adjust the ride height, improving aerodynamics and accessibility. And now on to performance metrics. Ride comfort, a crucial metric that evaluates how effectively the suspension system isolates the occupants from road irregularities and vibration. Handling. This evaluates the vehicle's stability and responsiveness during cornering, acceleration, and braking, significantly impacted by the suspension design. Durability, the longevity and maintenance requirements of the suspension system critical for the overall reliability and cost of ownership of the vehicle. Noise, vibration, and harshness. The suspension system plays a pivotal role in managing the levels of noise, vibration, and harshness experienced within the vehicle, enhancing the overall ride quality. Broader implications of suspension design extend to vehicle safety. A well-designed suspension system ensures that the wheels maintain contact with the road, providing the necessary traction control, especially during emergency maneuvers. Moreover, the suspension system contributes to the overall aerodynamics of the vehicle, impacting fuel efficiency and performance. The ability to adjust the ride height and suspension settings can significantly improve a vehicle's aerodynamic profile, reducing drag and enhancing fuel efficiency. As we delve into the nexus between suspension systems and other vehicle systems in subsequent lectures, the symbiotic relationships that underpin the holistic design and performance of modern vehicles will become increasingly apparent. So, as we spring forth into the ensuing chapters of our automotive saga, let's carry forth the understanding glean, ready to unravel further intricacies of automotive engineering. Today we navigate towards another pivotal facet of automotive engineering, the steering systems. The steering system is akin to the navigator of a vehicle, translating the driver's inputs into directional changes. It's a marvel of mechanical and, in modern vehicles, electronic engineering that ensures precise control and safe maneuvering of the vehicle on the road. Let's embark on our discussion by understanding the core components of a steering system. Steering wheel, the primary interface between the driver and the steering system, translating the driver's inputs into mechanical or electronic signals. Steering column. This is a shaft connecting the steering wheel to the steering gear, often housing additional controls like turn signals and ignition switches. Steering gear. This crucial component translates the rotational movement of the steering wheel into the lateral movement required to turn the wheels. The most common types are the rack and pinion and the recirculating ball steering gears. Steering linkages. These include tie rods, arms, and joints that transfer the motion from the steering gear to the wheels, ensuring accurate wheel alignment. Power steering system. Modern vehicles are equipped with power steering systems that assist the driver in turning the wheels, making steering much easier and more precise. Now, transitioning to modern advancements, we have electronic power steering systems. It replaces the hydraulic assist of traditional power steering with an electric motor, providing precise control while reducing weight and improving fuel efficiency. Adaptive steering. This technology adjusts the steering ratio based on vehicle speed, providing a more direct steering feel at higher speeds and easier maneuvering at lower speeds. Steer by wire, an emerging technology that eliminates the mechanical linkages altogether, replacing them with electronic controls and actuators. This allows for more flexible vehicle designs and further enhances steering precision and feedback. Performance metrics for steering systems include steering ratio. The ratio of the number of degrees the steering wheel is turned to the number of degrees the wheels turn. A lower ratio provides quicker steering response. Turning radius, the smallest circular turn a vehicle can make, crucial for maneuverability in tight spaces. Steering effort, the amount of force required to turn the steering wheel, a critical metric for driver comfort and control. Feedback, the information transmitted back to the driver through the steering wheel, providing a sense of the road conditions and vehicle dynamics. The evolution of steering systems mirrors the broader narrative of automotive engineering, striving for enhanced safety, precision, and user-centric design. Modern advancements like electronic and adaptive steering are significantly enhancing the driving experience, offering a more intuitive and safe interaction between the driver and the vehicle. Today, we delve into a paramount aspect of automotive engineering, the braking systems. The braking system is the guardian of vehicle safety, providing the essential function of decelerating and halting the vehicle. It's a blend of mechanical, hydraulic, and electronic components, all working in tandem to ensure a safe and controlled cessation of motion. Let's initiate our examination with the central components of a braking system. Brake pedal, the interface between the driver and the braking system, translating the driver's input into a mechanical or hydraulic action. The master cylinder, when the brake pedal is depressed, the master cylinder generates hydraulic pressure, which is transmitted to the brakes. Brake lines and hoses. These conduits transfer the hydraulic fluid from the master cylinder to the brakes, ensuring a secure and reliable pathway. Brake calipers and wheel cylinders. These components apply the hydraulic force to the brake pads and shoes, creating the friction needed to slow down the wheel. Brake pads and shoes, the materials that create friction with the brake, discs, and drum to slow down or stop the vehicle. Brake discs and drums, the rotating components that are slowed down or stopped by the friction from the brake pads and shoes. Now, veering towards modern advancements, we have anti-lock braking system, as prevents lockup during braking by modulating brake pressure, improving vehicle control, and reducing stopping distances on slippery surfaces. Electronic brake force distribution ABIS system optimizes brake force between the front and rear wheel based on load conditions, enhancing braking effectiveness. Brake assist by detects emergency braking situations and increases braking pressure to maximize stopping performance. Regenerative braking, utilized in electric and hybrid vehicles. Regenerative braking recovers energy during deceleration, converting it into electrical energy, which is stored in the battery for later use. Performance metrics for braking systems encompass stopping distance, the distance a vehicle travels from the point when the brakes are applied to when it comes to a complete stop. Brake fade, the reduction in braking effectiveness due to overheating or other factors, a critical consideration for brake material and design. Pedal feel, the feedback felt by the driver through the brake pedal, providing a sense of braking effectiveness and control. Noise and vibration, undesirable attributes in the braking system which can be mitigated through careful design and material selection. The design and operation of braking systems are a testament to the rigorous engineering and safety considerations that underpin automotive design. The advent of electronic controls and regenerative braking technology showcases the ongoing evolution aimed at enhancing safety, efficiency, and performance. As we break our way through this vital domain, the knowledge acquired here will form a bedrock for understanding the intertwined safety system and the holistic approach to vehicular safety and control. So, with a steadfast grip on the knowledge gained, let's decelerate our pace to halt today's discourse, ready to accelerate into new realms of automotive engineering and our subsequent meetings. Today, we turn our focus towards the domain of vehicle safety systems, a cornerstone of automotive engineering dedicated to protecting occupants and mitigating the severity of accidents. As vehicles have evolved, so too have the systems designed to ensure their safe operation, reflecting a broader commitment within the automotive industry towards enhancing safety on the roads. Let's commence our examination with the primary categories of vehicle safety systems. Passive safety systems. These are designed to protect occupants when an accident occurs. Key components include airbags, cushioning devices that inflate upon collision, providing a buffer to reduce the impact of occupants. Seatbelts, restraint systems that keep occupants securely in place, minimizing movement during a crash. Crumple zones, design areas of a vehicle that deform and absorb energy during a collision, reducing the force transfer to occupants. Active safety system. These systems aim to prevent accidents from occurring in the first place. Noteworthy advancements include anti-lock braking system, prevents wheel lockup during hard braking, maintains steering control. Electronic stability control prevents skidding and loss of control by automatically applying brakes to individual wheels if necessary. Traction control system prevents whiplash during acceleration by reducing engine power or applying brakes to individual wheels, ensuring optimum grip. Driver assistance systems. These systems provide assistance to the driver, enhancing safety and ease of driving. Significant systems include adaptive cruise control. Maintains a set speed while adjusting to keep a safe distance from vehicles ahead. And lane keeping assist helps keep the vehicle centered within its lane by providing corrective steering inputs. Blind spot monitoring alerts the driver to vehicles in the blind spots, enhancing situational awareness. Advanced driver assistance systems, these are sophisticated systems that provide a higher level automation, significantly enhancing safety and convenience. Examples include automated emergency braking automatically applies the brakes to prevent a collision or reduce collision severity if a pending crash is detected. Self-parking systems assist the driver in parking maneuvers, reducing the risk of collision. Safety in automotive design is not merely about individual systems, but entails a holistic approach that integrates these systems into a cohesive unit, working in unison to provide a safe and secure driving environment. The continuous advancements in vehicle safety systems underscore the automotive industry's relentless pursuit of reducing accident rates and enhancing the well-being of all road users. As we steer into the intricacies of these safety systems in subsequent discussion, the insight garnered will serve as a lighthouse, illuminating the paramount importance of safety in automotive engineering and the innovative strides being made in this realm. So, let's harness the knowledge accumulated and buckle up as we drive forward into the captivating world of automotive safety systems, ready to explore the myriad innovations that stand as sentinels of safety on our roads. As we venture into the final lecture of this series, we shall delve into the domain of automotive electronics and control systems, a realm that has witnessed a profound transformation over the decades. The modern vehicle is a marvel of electronic innovation with a myriad of sensors, controllers, and actuators working in a harmonized fashion to enhance performance, safety, and convenience. Let's begin by outlining the primary categories of automotive electronics. On engine control unit, the brain behind engine operation, managing aspects like fuel injection, ignition timing, and air-fuel mixture to ensure optimal performance and efficiency. Transmission control module governs the operation of the transmission, ensuring smooth gear shifts and optimal gear selection based on driving conditions. Body control module manages various body-related functions like light and central locking and window operation, enhancing convenience and safety. Safety control systems encompass systems like anti-lock braking system and electronic stability control and stay working tirelessly to enhance vehicle safety. Driver assistance and informant systems encompass a wide range of systems providing entertainment, navigation, and driver assistance to enhance the driving experience. Now let's delve into some modern advancements. Onboard diagnostics provides insightful diagnostics and monitoring of vehicle subsystems, aiding in maintenance and troubleshooting. Adaptive control systems such as adaptive cruise control action, adaptive lighting, which adjust their operation based on real-time conditions to enhance safety and convenience. Vehicle connectivity incorporates systems like vehicle-to-vehicle and vehicle-to-infrastructure to communication, paving the way for intelligent transportation systems. Autonomous driving technologies encompass a spectrum of technologies enabling varying levels of vehicle automation, from driver assistance systems to fully autonomous vehicles. Performance metrics for automotive electronics and control systems encompass reliability, the robustness and dependability of electronic systems, crucial for safety and performance. Responsiveness, the speed and accuracy with which systems respond to inputs and changing conditions. Efficiency, the ability to enhance vehicle performance and fuel efficiency through precise control and optimization. User-friendliness, the ease of interaction between the driver and the vehicle's electronic systems, impacting the overall driving experience. The proliferation of electronics and automotive design reflects a broader narrative of technological innovation driving the evolution of modern vehicles. The integration of sophisticated control systems, connectivity solutions, and autonomous driving technologies represents the cusp of a new era in automotive engineering. As we conclude our automotive expedition, the understanding amassed throughout this series lays a solid foundation for appreciating the multifaceted nature of automotive engineering. The journey traversed serves as a precursor for deeper exploration in specialized domains, each holding a universe of knowledge ready to be unraveled. So with the ignition of curiosity kindled and the throttle of enthusiasm engaged, let's drive forward into the vast expanse of knowledge awaiting us beyond the horizon, ever ready to explore, learn, and innovate. Today we embark on a journey to explore the heart of traditional automotive propulsion, the internal combustion engine. A story of internal combustion engines dates back to the 19th century, with Etienne Lenoir crafting the first gas-fired internal combustion engine in 1860. Over the years, this remarkable invention has powered our automobiles, contributing significantly to the industrial and transportation revolution that shaped the modern world. Now let's dissect the term internal combustion engine. The process happens internally within an engine's cylinders where a fuel-air mixture is combusted, producing high temperature, high pressure gases that exert force on the engine's pistons, driving them to move. This motion is what eventually powers your car to drive down the road. The realm of internal combustion engines is vast, but primarily we have two types: spark ignition engines, which are typically gasoline fueled, and compression ignition engines, usually powered by diesel. The distinction lies in the initiation of combustion. Inside engines, a spark plug ignites the air-fuel mixture, whereas in G engines, combustion begins due to the high temperature achieved from compressing the air-fuel mixture. Silent and C engines have found their niches, with Chi engines traditionally dominating the passenger car market due to their quiet operation and lower emissions, while Chi engines have been the choice for heavier vehicles like trucks and buses due to their higher efficiency and torque. The essence of internal combustion engines extends beyond just the engine types. It encapsulates an array of technologies and components, each meticulously designed to optimize performance, efficiency, and emissions. From the intricacies of fuel injection systems ensuring the precise delivery of fuel, the art of tuning an engine to balance power and efficiency, to the advent of turbocharging, boosting engine power, the domain of internal combustion engines is a blend of mechanical ingenuity and evolving technologies. Moreover, the significance of internal combustion engines isn't confined to powering vehicles alone. They play a critical role in various sectors, powering airplanes, generators, and even marine vessels. The widespread application of internal combustion engines underscores their importance in our modern day lives. As we delve deeper into the realm of internal combustion engine, it's imperative we familiarize ourselves with the basic terminology and concept that form the lexicon of this domain. These terms provide a language through which we can understand and discuss the intricate workings of engines. Let's start with engine configurations. Engines are arranged in various configurations, each with its unique set of advantages. The straight or inline configuration has cylinders arranged in a straight line, simple in design and easy to maintain. The V configuration, with its cylinders arranged in two banks forming an aven, is more compact and can house more cylinders in a smaller space. The flat or boxer configuration has its cylinders arranged horizontally, lowering the center of gravity and improving stability. Now, let's talk about engine displacement, term that signifies the total volume of all the cylinders in an engine measured in cubic centimeters, key, or liters. It's a fundamental indicator of an engine size and potential power output. Bigger displacement often translates to more power, but at the expense of fuel efficiency. The terms bore and stroke are central to understanding engine geometry. The bore is the diameter of the engine cylinder, while the stroke is the distance the piston travels from its lowest to highest point. The ratio of bore to stroke affects the character of the engine, impacting its efficiency, power, and torque characteristics. Now, on to a crucial term, compression ratio is the ratio of the maximum to the minimum volume in the cylinder. A higher compression ratio means the air-fuel mixture is compressed more, often leading to higher thermal efficiency, but it also requires higher octane fuel to prevent knocking. Transitioning to the heart of the engine, the combustion chamber is where the magic happens. It's the space enclosed by the cylinder, piston, and cylinder head where the combustion of the air-fuel mixture occurs. The design of the combustion chamber, its shape and size play a pivotal role in determining engine efficiency and emissions. As we venture into the various system and components in the subsequent lecture, these terms will recur, forming the backbone of our discussions. The engine block, often referred to as the heart of the vehicle, houses the cylinders and other components like the crankshaft and camshaft. The crankshaft transforms the linear motion of the pistons into rotational motion, which eventually drives the wheels. Camshaft, on the other hand, operates the intake and exhaust valve, ensuring the timely flow of air, fuel, and exhaust gases in and out of the combustion chamber. These terms and concepts form the basic vocabulary necessary to delve deeper into the intricacies of internal combustion engine. As we transition from the rudimentary to the more complex, having a solid grasp of these fundamental terms will serve as the stepping stones for a deeper understanding of the multifaceted world of internal combustion engines. As we steer forward in our exploration, it's time to delve into the core mechanics of how internal combustion engines operate. The mesmerizing dance of pistons and valves, orchestrated by a symphony of mechanical and thermodynamic principles, is what propels our vehicles forward. Let's initiate our discussion with the four-stroke cycle, a common operating cycle of many modern engines. The name derives from the four distinct piston strokes that occur in a sequence: intake, compression, combustion, and exhaust. During the intake stroke, the piston descends from the top to the bottom of the cylinder, creating a vacuum that draws in a fresh charge of the air-fuel mixture through the open intake valve. The exhaust valve remains closed during this phase. Next comes the compression stroke, where both valves close and the piston ascends, compressing the air-fuel mixture into a tight bundle of potential energy, ready to be ignited. The magic happens during the combustion stroke. As the piston approaches the top of the cylinder, a spark plug ignites the compressed air-fuel mixture, unleashing a fiery expanse of gas that pushes the piston back down with great force, generating the power that drives the engine. Lastly, the exhaust stroke sees the exhaust valve opening and the piston ascending once more, expelling the spent combustion gases out of the cylinder, making room for a fresh charge of the air-fuel mixture in the next cycle. Now, let's shift gears and talk about the two-stroke cycle, a simpler yet powerful alternative. Unlike its four-stroke cousin, the two-stroke engine completes the same four processes, but in just two piston strokes. In a two-stroke engine, as the piston moves upwards, it compresses the air-fuel mixture, which is then ignited by a spark plug. The resulting explosion forces the piston down, which simultaneously opens the exhaust port to expel burnt gases and uncovers the intake port to draw in a fresh charge of the air-fuel mixture, ready for the next cycle. This design allows two-stroke engines to generate power on every revolution of the crankshaft, doubling the power output compared to a four-stroke engine of the same size. However, the simplicity and power of two-stroke engines come with downsides. Notably, they are less fuel efficient and their emissions are less environmentally friendly due to incomplete combustion and oil mixing with fuel for internal lubrication. The choice between four-stroke and two-stroke engines is a trade-off. One offering efficiency and cleaner emissions, the other offering simplicity and higher power output. The application dictates the choice. For instance, lawnmowers and dirt bikes might favor the two-strokes power and simplicity, while cars and trucks lean towards the four-stroke efficiency and lower emissions. The fundamental processes, intake, compression, combustion, and exhaust, are the heartbeats of internal combustion engines, a rhythmic cycle that has powered our vehicles across billions of miles, connecting cities, countries, and continents. Today, we dive into the realm of spark ignition engine, a type of internal combustion engine that's primarily powered by gasoline, although other fuels like ethanol or gaseous fuels can also be utilized. The moniker spark ignition derives from the mechanism of igniting the air-fuel mixture within the combustion chamber using a spark plug. Let's delve into the intricacies that underpin the operation and characteristics of SI engines. The heart of the SI engine's operation lies in the induction of a mixture of air and fuel into the combustion chamber, followed by the ignition of this mixture through a spark created by the spark plug. This contrasts with compression ignition engines, where fuel injection and self-ignition occur due to the high temperature achieved through air compression. Now, let's delve into the fuel systems. Traditional SI engines utilize carburetors to mix air with fuel to create a combustible mixture. The carburetary mechanical device was simple but not very precise, often resulting in inefficiencies and suboptimal combustion. Modern SI engines, on the other hand, employ fuel injection systems that provide precise metering of fuel, ensuring an optimal air-fuel ratio for combustion. Fuel injectors, controlled by the engine's electronic control unit, deliver fuel directly into the intake manifold or the combustion chamber, allowing for more accurate fuel delivery and better control over the combustion process. Now, on to ignition system. The ignition system primary role is to generate a spark at the spark plug, igniting the air-fuel mixture. Early ignition systems use mechanical distributors to time the spark, but modern systems use electronic ignition, where sensors in the engine control unit manage the timing and distribution of sparks. This electronic control enables better timing accuracy, improving engine efficiency and performance. The air-fuel mixture's ignition timing is critical for optimal engine performance. Advanced ignition, where the spark occurs earlier in the engine cycle, can improve performance but risk causing engine knocking. Conversely, retarded ignition, where the spark occurs later, can prevent knocking but at the expense of performance and efficiency. The evolution from carburetor to fuel injector and from mechanically controlled to electronically controlled ignition system underscores the broader narrative of technological advancement, enhancing engine performance, efficiency, and emissions control. These advancements reflect the relentless pursuit of engineering excellence, aiming to extract every ounce of performance while minimizing environmental impact. Today, we traverse the landscape of compression ignition engines, a domain where combustion is instigated not by spark, but by the sheer force of compression. Commonly fueled by diesel, these engines are a hallmark of efficiency and robustness, finding their place in larger vehicles and heavy-duty applications due to their substantial torque and durability. Diving into the mechanics and the engine. Air alone is drawn into the combustion chamber during the intake stroke. This air is then compressed to a high pressure and temperature during the compression stroke. Post-compression, fuel is injected into the combustion chamber where it out ignites due to the elevated temperature of the compressed air. This contrasts starkly with spark ignition engines where a mixture of air and fuel is inducted and ignited by spark. Now, let's shed light on fuel injection systems, which are the heart of SI engines. The preciseness of fuel injection, both in terms of quantity and timing, is paramount for optimal combustion. Modern SI engines employ electronic fuel injection key systems governed by an engine control unit CUB, which meticulously controls the fuel injection process, ensuring the right amount of fuel is injected at the right time, optimizing both combustion and emissions. Transitioning to combustion chambers, the design plays a pivotal role in ensuring effective combustion and minimizing emissions. In jet engine, the combustion chamber is where the compressed air meets the injected fuel, igniting to release energy. The shape and design of the combustion chamber, the placement of the fuel injectors, and the spray pattern of the injected fuel are all meticulously engineered to promote efficient mixing and combustion, minimizing burnt fuel and emissions. Engines are revered for their efficiency and torque. The high compression ratio of SI engines leads to better thermal efficiency, meaning a larger portion of the fuel's energy is converted into useful work. Moreover, the inherent design of SI engines provides substantial torque, making them suitable for heavy-duty applications where high pulling power is essential. However, SI engines aren't without their challenges. The high compression ratios can lead to engine knocking, and the combustion process in SI engines tends to produce more nitrogen oxides, a significant pollutant. Modern science engines, however, have made strides in mitigating these issues through advanced fuel injection systems, exhaust after treatment, and other engineering innovations. Today's discourse orbits around the core components and materials that form the structural and functional anatomy of internal combustion engines, the synergy between various engine components and the materials from which they are crafted underpins the engine's performance, durability, and efficiency. That's comments would delve into some primary engine components. For instance, pistons are cylindrical components that move up and down within the engine cylinders, a motion instigated by the combustion process. The top of the piston, known as the crown, faces the combustion chamber, enduring the brunt of the combustion forces, while the sides ensure a snug fit within the cylinder, minimizing leakage and promoting efficient transfer of forces. Connecting rods. These rods act as the linking entities between the pistons and the crankshaft, transmitting the forces generated during combustion from the pistons to the crankshaft, thus converting linear motion into rotational motion, minimizing friction between moving parts, dispersing heat, and ensuring the longevity of engine components. Splash lubrication in this rudimentary system. Dipper on the connecting rod cap splashes oil onto engine components as it moves. While simple, its effectiveness is limited to lower speed, lower load applications. Pressure lubrication. A more advanced system, pressure lubrication, employs an oil pump to circulate oil under pressure to bearings, bushings, and other critical surfaces. It provides a reliable supply of oil to engine components, ensuring smooth operation under a wide range of conditions. Dry wet sump lubrication. Engines may employ a wet sump where an oil reservoir is integrated into the engine, or a dry sump where oil is stored in a separate tank and pumped into the engine. Dry sump systems, though more complex, provide better oil control under high performance or racing conditions. The harmony between cooling and lubrication systems is fundamental in orchestrating the symphony of mechanical interactions within an engine. The meticulous design of these systems, coupled with advancements in materials and fluids, exemplifies the relentless pursuit of engineering perfection, each innovation contributing to enhanced engine performance, efficiency, and longevity. Today's voyage takes us into the numerical realm of engine performance metrics, the indicators that help us gauge the potency, efficiency, and operational quality of internal combustion engines. These metrics are the language through which we communicate and evaluate engine performance, providing a quantitative lens to view the outcomes of design choices and technological advancements. Let's start with the powerhouses of performance metrics: power and torque. Power, often expressed in horsepower or kilowatts. Power represents the rate at which work is done or energy is transferred. In engines, it's the rate at which fuel's energy is converted into mechanical energy. A higher power rating often translates to higher top speeds and faster acceleration. Torque, measured in Newton meters, pound-feet. Torque represents the rotational force produced by the engine. It's the torque that propels your vehicle from a standstill and helps it climb hills. High torque is especially prized in heavy-duty vehicles and trucks for their pulling and hauling capabilities. Now, bridge to efficiency, the thermal efficiency. Thermal efficiency. This metric reflects how well an engine converts the energy stored in fuel into mechanical energy or work. Higher thermal efficiency indicates a better conversion rate and consequently better fuel economy. Diving into the specific power metrics, brake horsepower, this is the engine's output. Before us is like friction, and is often higher than the horsepower that reaches the wheels, known as wheel horsepower. The indicator horsepower this reflects the power produced directly by combustion, offering a glimpse into the engine's raw potential before mechanical losses. Mechanical efficiency, a ratio of BP to IPI. This metric highlights how effectively the engine converts combustion power into mechanical power. Moving on to engine speed. Liters per minute. AP, a measure of how many times the crankshaft rotates in a minute, indicating the engine's operational speed. Lastly, the emissions narrative. Emissions ratings. With growing environmental concerns, reducing emissions is paramount. Metrics like grams per kilometer of CO2 or the level of nitrogen oxide, NOx, emitted are critical in evaluating and improving the environmental footprint of engine. These metrics are not standalone. They intertwine to narrate the performance story of an engine. For instance, an engine may boast high power, but at the cost of fuel efficiency or emission compliance. The engineering challenge lies in optimizing these metrics, a delicate balancing act to achieve a blend of performance, efficiency, and environmental compatibility. Today's exploration propels us into the heart of internal combustion, minimizing friction between moving parts, dispersing heat, and ensuring the longevity of engine components. Splash lubrication in this rudimentary system. Dipper on the connecting rod cap splashes oil onto engine components as it moves. While simple, its effectiveness is limited to lower speed, lower load applications. Pressure lubrication. A more advanced system, pressure lubrication, employs an oil pump to circulate oil under pressure to bearings, bushings, and other critical surfaces. It provides a reliable supply of oil to engine components, ensuring smooth operation under a wide range of conditions. Dry wet sump lubrication. Engines may employ a wet sump where an oil reservoir is integrated into the engine, or a dry sump where oil is stored in a separate tank and pumped into the engine. Dry sump systems, though more complex, provide better oil control under high performance or racing conditions. The harmony between cooling and lubrication system is fundamental in orchestrating the symphony of mechanical interactions within an engine. The meticulous design of these systems, coupled with advancements in materials and fluids, exemplifies the relentless pursuit of engineering perfection, each innovation contributing to enhanced engine performance, efficiency, and longevity. Today's voyage takes us into the numerical realm of engine performance metrics, the indicators that help us gauge the potency, efficiency, and operational quality of internal combustion engines. These metrics are the language through which we communicate and evaluate engine performance, providing a quantitative lens to view the outcomes of design choices and technological advancements. Let's start with the powerhouses of performance metrics: power and torque. Power, often expressed in horsepower or kilowatts. Power represents the rate at which work is done or energy is transferred. In engines, it's the rate at which fuel's energy is converted into mechanical energy. A higher power rating often translates to higher top speeds and faster acceleration. Or measured in Newton meters, pound-feet. Torque represents the rotational force produced by the engine. It's the torque that propels your vehicle from a standstill and helps it climb hills. High torque is especially prized in heavy-duty vehicles and trucks for their pulling and hauling capabilities. Now, bridge to efficiency, the thermal efficiency. Thermal efficiency. This metric reflects how well an engine converts the energy stored in fuel into mechanical energy or work. Higher thermal efficiency indicates a better conversion rate and consequently better fuel economy. Diving into the specific power metrics, brake horsepower, this is the engine's output before forces like friction, and is often higher than the horsepower that reaches the wheels, known as wheel horsepower. The indicator horsepower are half. This reflects the power produced directly by combustion, offering a glimpse into the engine's raw potential before mechanical losses. Mechanical efficiency, a ratio of BP to IPI. This metric highlights how effectively the engine converts combustion power into mechanical power. Moving on to engine speed. Liters per minute. AP, a measure of how many times the crankshaft rotates in a minute, indicating the engine's operational speed. Lastly, the emissions narrative. Emissions ratings. With growing environmental concerns, reducing emissions is paramount. Metrics like grams per kilometer of CO2 or the level of nitrogen oxide NOx emitted are critical in evaluating and improving the environmental footprint of engine. These metrics are not standalone. They intertwine to narrate the performance story of an engine. For instance, an engine may boast high power, but at the cost of fuel efficiency or emission compliance. The engineering challenge lies in optimizing these metrics, a delicate balancing act to achieve a blend of performance, efficiency, and environmental compatibility. Today's exploration propels us into the heart of internal combustion.